12s. Welcome to module number 27, and in this module we're going to cover pages 25 to 28. Really, there's only 3 pages there, and it's a couple of new calculations, okay? So it might be a little bit tricky, and if you want to do some of the textbook questions, you can, and in the review package you could now do questions 6 to 9. So just do as much or as little as you think, and I think this will make sense, but it's a little bit tricky because we're going to start adding on to our Ksp. So we're back to Ksp, and now we're going to look at what would happen if you added a salt to a solution and it's not just water. So how is the solubility going to be affected if there's ions in that solution that are the very same ions that you're adding in? So for example, if I was adding sodium chloride to a solution that already had sodium ions in it, it's not going to be able to dissolve as well as if I just add it to water. Does that make sense? So it's this thing called the common ion effect, and that's going to be what we do on pages 27 and 28. Okay, so what we're going to do right now on page 25 is look at, are there enough ions in the solution in order to actually make a precipitate? So this is like, I'm going to take zinc nitrate, add it to some barium hydroxide, and I know I'm going to get barium nitrate, which is soluble because it's got good solubility, follows the rules. It's got nitrates in there, but zinc hydroxide, okay, is it going to be a solid or not? In other words, it's slightly soluble. Is there enough of the ions there in order for it to make a precipitate? So all we're going to do is we're going to calculate the concentration of the zinc ions, and we're going to calculate the concentration of the hydroxide ions, and we're going to look at those concentrations. Once we've calculated those, put them into a Ksp expression, but we're just going to call it Q, again, because we don't know if there's enough ions there in order for it to be soluble or make a precipitate, and then we can just compare it to the Ksp. Okay, so here we go. We're going to write the balanced chemical equation, and we'll determine if a potential precipitate forms. Then we're going to determine the individual concentrations of the 2 ions that collide, okay, to produce the potential precipitate. Remember, the volume of the resulting solution, because we're looking at 2 different ions coming together from 2 different solutions into a container, we're going to use the total volume that we've got in the volumetric flask as our total volume. So that's the only part that's a little bit different from everything that we've been doing so far. And so this can potentially cause some concern for people, right? Because we've been doing stoichiometry where we've been calculating the concentration of the acid, and then we know the volume and figuring out the base. So we've been doing that, basic stoichiometry. This is a little bit different. This is just figuring out, do we have enough of the ions in the solution that we've made in order for a precipitate to form? Okay, so note that that's one big difference. Then you're going to substitute the concentrations of those ions into the Ksp. And then here's what we do with the Ksp. If we figure out that Q is greater than Ksp, then the sample produced exceeds the allowable concentration predicted by the constant, and guess what? A precipitate will form because there's enough there. The resulting mixed solution is temporarily more than saturated, and excess ions will precipitate out until the ion concentration meets the Ksp max. The excess precipitates out until the solution is saturated. Okay, and if we find that once we've got the ion concentrations and we put them into the Ksp expression, we find that Q is way less than Ksp, then you conclude that the sample product is less than the concentrations required to make a precipitate, and a precipitate therefore will not form. So the solution, how would you describe that solution then? It's not saturated, it's unsaturated. Okay, so here's what that looks like, and there's a little picture here that explains it. So the first thing we did was we write our balanced chemical equation, double displacement. You look at the solutes that form at the end, the solutions that form, and then we figure out which one is the potential precipitate? We don't know. So therefore, we know that we're going to use the zinc concentration of the ions and the concentration of the hydroxide ions that are going to be in my solution, and we're going to be able to put those concentrations into the Ksp. We just ignore the barium nitrate. It's not doing anything, right? So, completely soluble. So if you were to calculate that, it's not answering any part of this question. So here's your picture. You get your hydroxide ion concentrations from the barium hydroxide, and you get your zinc ion concentration from the zinc nitrate. But the only trick, remember, is that when you're calculating the concentrations of the two solutions mixed together, you're using the total volume. All right, so how would you set that up? Well, you know, based on the information in the question, you've got a volume of zinc nitrate and you know the concentration. You can clearly calculate the moles per liter. You've got your barium hydroxide. So I've already done this one for you, but again, remember you need to have the total volume. So I've got 0.1 liters of our zinc nitrate multiplied by my concentration that I had, which was 0.95 moles per liter. And I know that I've got 1 mole of zinc ions per 1 mole of zinc nitrate. Divide the whole thing by 0.1500 liters, and you're left with the concentration of my zinc ions. Let's do the same thing for calculating the concentration of my hydroxide. So pause the video and see if you can do it before you look at the solution. Okay, again, I've got this time I only had 0.05 liters of my barium hydroxide. The concentration of the barium hydroxide was 1.2 times 10 to the negative 5 moles per liter. And sorry, this is a little bit, I must have run out of space here. I've got 2 moles of hydroxide per 1, this is really messy, per 1 mole of barium hydroxide, right? 2-to-1 ratio. I've got 2 moles of that per, okay? Divide it all by your total volume again, which was 0.1500 liters, and now I have the concentration of my hydroxide ions. So now let's set it up and see if there's enough of those concentrations and compare it, right? Compare it to the Ksp. So let's show what that equation looks like so that we can set up our Ksp expression. Remember how to do this? Concentration of your products, they're both aqueous, so I've got my zinc concentration multiplied by my hydroxide concentration, and of course that's squared. So what do? I take the concentrations that I have just calculated up above, and I put those into my expression, and we're going to call it Q. Why? Because we don't know if there's enough there to be called the Ksp. And you can see that I already snuck the number in down here. That, of course, where do you get that? From the textbook, right? You get that from the table that tells you what the Ksp values are. So let's see if we had enough zinc ions and hydroxide ions, should be a negative there, in order to make a precipitate. So my zinc ion concentration from up above was 6.3 times 10 to the negative 2. My hydroxide concentration I calculated to be 8.0 times 10 to the negative 6. That is squared, right? Where did that square come from? Don't forget, there is 2 moles to 1 mole up above. So keep calculating. You would get 4.0 times 10 to the negative 12, and I just factored in there that you would be having an answer with 2 significant digits. So if you do that on your calculator, you'll get 4.03 times 10 to the negative 12. Okay, now I've got my Q value, I've got my quotient. Let's see, how does the Q compare to the Ksp? Well, what's bigger? There's my Q, there's my Ksp. What do we find out? That our Q value is bigger? Yep, greater than our Ksp. Therefore, yes, a precipitate will form. Okay, does that make sense? And so the solution must be saturated with enough zinc and hydroxide ions for the precipitate to form. Okay, that's it for that kind of calculation question. Oh no. Yeah, That's it. That's it for that one. Okay, let's move on. So what did we do right here? We were predicting whether a precipitate forms when solutions mix. And what do you have to remember? That when you're calculating your concentrations, this is the only kind of question that we do where you need the total volume of the solution, and so you add the two volumes of your reactants together. Okay? All right, skipping ahead then, let's move on to this next one. And this is what I mentioned at the beginning here. We are going to quantify this common ion effect, okay? Let's describe, and I've already jotted this down. Page 477 in your textbook. Because of Le Chatelier's principle, when we have a slightly soluble salt is dissolved in a solvent that contains one of the same ions that is already in the solution, a dissociation equilibrium is going to be affected. So this is like saying, I want to dissolve magnesium nitrate in a flask, but there's already magnesium in there. I'm clearly not going to be able to dissolve as much. And it all has to do with Le Chatelier's principle. In other words, if there's already magnesium in the solution, I can't dissolve as much magnesium nitrate as I would if there was just water. Okay? Common ion effect. That's your header for this section. So let's see what this looks like. Here we go. It is obviously an application of Le Chatelier's principle. So hence the equilibrium part 2 label that we put on to this lesson, or for the unit. An application of Le Chatelier, when a slightly soluble salt, here's one, dissolves in a solution that already contains one of the same ions. So let's say we put it into magnesium nitrate. Here's the equilibrium, right? Let's see how much until it makes a precipitate. So equilibrium symbol, magnesium carbonate going to magnesium ions and carbonate ions. What is the stress placed on this equilibrium system? Well, it's because you had magnesium nitrate. So the magnesium nitrate ions, that's the common ion in this equilibrium. In other words, what's the stress? An increase in the concentration of the magnesium ions. It's going to shift the equilibrium. Which way? Here's your magnesium. Increase the concentration. It's going to shift to the left. Okay? Does that? Oh, my arrow's not very good. Shift to the left. Net effect, you're going to decrease the solubility of magnesium carbonate when you dissolve it in a solution of magnesium nitrate. So let's compare the values. So the first part of this question here is already done for you because it's like the very first day, second day's lesson where we did last week, where we're just like, what's the molar solubility of magnesium carbonate? And we only did these kinds of questions with water, right? So what did we do? We write our little expression, we write our Ksp, we solve for our Ksp value, and we find that if you dissolve magnesium carbonate in water, you have a solubility of 2.6 times 10 to the negative 3 moles per liter. Not a very strong solution, right? It's slightly soluble. Okay, and that, when it's the Ksp, is when it's at equilibrium, because that's when an equilibrium expression will get set up. Now, how do we factor this in? Yikes, there's an ice table down below. So now let's calculate the molar solubility of magnesium carbonate in magnesium nitrate. So we're going to calculate what the solubility is here, and hopefully we're going to find that it's going to be less than this value that we calculated of the Ksp in water. Okay, so here we go. First thing I want you to recognize is when you've got your magnesium nitrate, we expect that 100% dissociation. Why? Because nitrate has good solubility. Therefore, 0.5 moles per liter of magnesium nitrate creates a concentration of magnesium to be 0.50 moles per liter, a 1:2 ratio. The concentration of my nitrate then is 2 times 0.5. That's equal to 1 mole per liter. Okay, now I've got a concentration of the magnesium ions that came from the magnesium nitrate. Let's put this information into an ice table. Okay, so we're going to calculate we're going to put in here, what are my concentrations of the magnesium and the carbonate ions? Okay, so we know that my magnesium concentration initially is already 0.5. Where did they come from? Those concentrated ions came from the magnesium nitrate. I don't have any carbonates, right? There's no carbonate in the solution yet, so that's 0. As the change happens, we know they both go up by a factor of 1. Magnesium carbonate had a 1-to-1 ratio, so it's plus X, let's solve for X. So my equilibrium concentration then isn't just X for magnesium, it's X plus what I already had to begin with. Okay, now this is tricky part number 2. Okay, what are we going to do here? I want to set up something that looks a little bit easy mathematically to figure out. So we're going to cheat and we're going to do an assumption on this value right here. Okay, we're going to carry the assumption through, assuming what we think, and then we're going to see if it actually works. Why? Because we want to do some easy math. Okay, so we're going to assume, here's our assumption. Let's say that the X value that we get is a lot less than my 0.5 that I'm going to be adding to it. In other words, let's say that 0.50 plus X is approximately equal to just 0.50. Okay? I'm going to just assume that this value is so small that it's not going to affect my significant digits of the 0.5. In other words, if it's 0.5000000029, it's pretty much the same as 0.5. When I calculate it out, just ignoring it, you're going to get the same answer. That's what my assumption means. Okay, this is hard. You're going to have to stop the video and go back and forth a couple of times. So let's do our Ksp calculation, assuming that the X is very small. Okay, so what do? I get my K value from the textbook, right? What is the Ksp? I pop in my calculation of my, right, concentrations for my ions, and I come up with a value for X. Now, this is the X that we just assumed was really small. Is that a really small number? 1.36 times 10 to the negative 5? Yes, it is. It's very small compared to 0.5, right? Imagine five zeros in front of that. If our assumption that X was so much less than 0.5, then I'm good to go. And I can just go with that answer and I don't have to do any other math, okay? Why does it work? Well, let's look right here. This is your table. This is what it says. We assumed that 0.00014 was a lot less than 0.5. Is it? Yes. If you added those two together, you're still going to get the same answer. So we saved ourselves some tricky math by just making an assumption. Okay? There's another problem later where you don't use the assumption. Here we go. So what do we do with these values? We calculated the molar solubility in water. We calculated the molar solubility in a solution with a common ion. Now let's compare those two values. Does a solution make it less soluble if you have an ion already there and accounted for? Let's compare, okay? So what are we comparing? Can you see those two values? The 2.6 times 10 to the negative 3 and the 1.36 times 10 to the negative 5. You are right. 1.36 times 10 to the negative 5 is a smaller number than 2.6 times 10 to the negative 3, right? This was the solubility in magnesium nitrate, and this was the solubility in water. And what did we find? We certainly found that if there's an ion already there, then you can dissolve less than you could if you were calculating the solubility in water. Okay, one more question. Let's do this one. Calculate the molar solubility of magnesium carbonate in 1.2 times 10 to negative 3 moles per liter of magnesium acetate. So we're going to start by using the assumption to prevent having to do the tricky math by using a quadratic. However, we solve this using the assumption and we find that the molar solubility, so our X value, is not way less than 1.2 times 10 to the 3. If that's the case, okay, here we go. You see the math here? We're like, we assumed that magnesium carbonate, there's our value that we popped in here for my initial magnesium ions. We made the assumption right here that it was going to be a lot less than 1.2 times 10 to the negative 3, and we solved it and got 5.6 times 10 to the negative 3. That is not less, right? In fact, it's greater than. I can't use my assumption for this question. It just means you have to solve it using the quadratic formula. And when you do, then you get an accurate read for the X value, which would be 2.1 times 10 to the negative 3. Okay? Therefore, actually that just shows you one more quick little example of how to do it. If you had to do it before, like let's say you did problem B, where you use the quadratic formula, would you get the same answer? Yes, you would. Okay, so it just shows that you can solve it with that X value in, but if you want to make it easy, make the assumption and factor that in. Okay, there are some textbook questions for this. Give it a go. If you want to do as much or as little as you need, right? Maybe just write down a problem and give one example of these kinds of problems. And then again, let's just try to do the questions from the review package. Okay, take care.